Alright, this video is going to be covering acids and bases. So we're going to start out with some definitions of an acid. And the first one is the Arrhenius definition. And Arrhenius says that an acid is a substance that produces H+ or H3O+ ions in water. And sometimes you'll see it written as H3O+. This is called the hydronium ion. So in this case, I have an acid, HCl, and it produces this H+ and Cl-, and it splits them into ions. So that defines it as an Arrhenius acid because it produces H+. Some properties of acids are that they have a sour taste, they turn blue litmus paper red, and they are generally corrosive. Now, as far as a base produces OH- ions in water. So if you can see the reaction down here, we have NaOH. When we dissolve it in water, I make Na+ and OH-. So since I make OH-, that's going to characterize it as a base. Other properties of bases is that they usually taste bitter, they feel soapy or slippery, they will turn red litmus paper blue, and they turn the phenolphthalein indicator pink. So some common bases. Most of our common bases have OH- in them, which is the hydroxide ion. And if we were going to name those bases, we would just name, those are all with a metal with OH. So sodium hydroxide, potassium hydroxide, barium hydroxide, aluminum hydroxide. In this case, iron is one of those that has to have that Roman numeral. So this would be iron 3 hydroxide. So if you see hydroxide in it and it's with a metal, that's going to clue you in that it's a base. All right, so we have talked so far about the Arrhenius acid. We said that they produce H+, and then a base produces OH-. And we talked about the taste, the feel, what they did in litmus paper, and then we talked about in a base that the phenolphthalein turns pink. We have not talked about Bronsted-Lowry yet, or neutralization. All right, so it says to identify each one of these as a characteristic of an acid or base. So you can pause the video and then come back to this after you've answered the question. So if it has a sour taste, that's an acid. If it produces OH, that's a base. A bitter taste is a base. And electrolytes means that they conduct electrical current. That is both acids and bases. And if it produces H+, then it's an acid. Okay, our second definition that we're going to look at is called Bronsted-Lowry. And according to Bronsted-Lowry, an acid is a proton donor. So I'm going to have the same reaction that we looked at before, except it was just H+ and Cl-. This time I can see that it's producing this H3O+ ion that's right here, that hydronium ion. So I can already tell that this is an Arrhenius acid because it produces that H+. But as far as Bronsted-Lowry goes, if I look at the HCl here, and then I look at what's left on the other side, I've lost an H on the other side, which means since it lost an H, that it is the H+ donor, the proton donor. That means that one is the acid. And here we can tell that the H donated it to the water. So I got H3O+ on this side. And then since it lost one, it made Cl-. Okay, the base is the one that is the proton acceptor. So in this case, I have NH3, and over here I have NH4+. So that means it gained an H. That H came from the water. So it made NH4+, and then since this lost the H, it made OH-. So since this one was the proton acceptor, that is the base. This is the proton donor, so that one was the acid. Okay, when we look at what's on one side and what's on the other, those are called conjugate acid-base pairs. So in every reaction, you're going to have two conjugate acid-base pairs. And each one is related to the other by either the loss or the gain of an H+. The conjugate acid is formed from the base accepting a proton, and the conjugate base is formed from the acid donating a proton. All right, so this one says write the conjugate base of the following. So we're going to go back here. A conjugate base is formed by the acid donating a proton. So in this case, if these are going to donate a proton, I'd get rid of the H and I would have Br minus. If I lost an H here, this would be HS minus. And if I lost a H here, this would be HCO3 minus. So in each case, I lose an H. Now in the second part, we want to write the conjugate acid. And remember, the conjugate acid is formed from the base accepting a proton. So if these accepted a proton, I would have HNO2. And since this is H+, it cancels out this minus. Here I would have NH4, and I gained a plus. And here if I had OH minus, I'm going to add another H. So I get H2O. And since H is a plus, it canceled out that minus. All right, in this one, they want me to find the conjugate base of HCO3. So the HCO3 is acting like an acid, so it's a proton donor. So I want the one that donates a proton. So that's going to have to be this one. The conjugate acid of this one means I'm going to add an H. So that would have to be C. And then the conjugate base of this one means it's going to lose an H. And the conjugate acid gains an H. And those are the answers that we got. Okay, so here I want to identify conjugate acid-base pairs. All right, so here's HI. And what's left when it donates an H is I minus. So that's one set. The other conjugate acid-base pair is these two, because here I had H2O and here I gained an H, so I had H3O plus. So HClO, and I want to find its partner on the other side, which differs by an H. That's that one. And then the other ones are these two because they differ by an H. So here, find its partner that differs by an H. That's that one. And then those two differ by an H. All right, when we talk about strong acids and strong bases later on, a strong acid means it completely separates into ions. And we can tell that we have a strong one because it's going to have a single arrow. Now, both of these ones have a double arrow, so both of these would be weak. If we wanted to look at like HCl, I have a single arrow right here. That's going to tell me that it's a strong acid. A weak acid only partially separates into ions. Some of those ions still stay together, and we're going to recognize that by having a double arrow, one that goes forward and backward. It's reversible. All right, now you're going to have to memorize the 6 strong acids. They're HCl, HI, HBr. Those are all from column 7, the Cl, the Br, the I. Then we have HNO3, which is nitric, H2SO4, which is sulfuric, and HClO4, which is perchloric. Now, those are the only 6 strong acids. Everything else is weak. All right, so that means since there's only 6 strong acids, that means most of the things are weak. Okay, a strong base. These are the alkaline metals. Remember, that's column 1. So that would be the lithium, the sodium, the potassium, the strontium. Those are all from the lithium, the sodium, and the potassium. Those are all from column 1. So an alkaline metal with OH, or the alkaline earth metals below calcium. That would be calcium, the barium, and the strontium. So these 3 are your alkaline earth, and these ones are your alkali. Okay, these ones separate completely, so the K separates from the OH. So that means if it's not strong, it's weak. So all of our other ones are weak bases, and they only separate a little bit. Some still stays together. And once again, we're going to recognize it by having a reversible arrow. A lot of your household products that are used to remove grease and open drains, those are going to be bases. So it just gives you some different examples there of bases that you're going to use in your home. All right, this one says to identify the following as strong or weak. These are from my list that I memorized in my head. So if you want to pause the video, then you can come back and check your answers. So HBr was on that list of strong. Nitrous acid came from nitrite. It's HNO3 nitric, that is the strong one. So with the HNO2, it's weak. NaOH is a strong base because that's with the alkali metal. H2SO4 is one of the strong acids we memorized. And CuOH2, Cu is not column 1 or not calcium and below in column 2, so it's not strong base, it must be weak. And I can tell acids from the bases because remember our bases have the OH and our acids have the H usually in the front. Okay, water tends to automatically split up into ions. So if I have one water reacting with another water, I'm going to make an H3O plus and an OH minus. So I can see that it's both a proton donor and a proton acceptor. It also produces H plus and it also produces OH minus. So it is both an acid and a base. And a substance that can act like both an acid and a base is called amphoteric. So it can act like both an acid and a base, depends on what it's with. All right, so when we look at Kw, Kw is called the ion product constant. And Kw means I can take my H3O plus ions times my OH minus ions. I can use, if I know the OH, I can find the H3O plus, or if I know the H3O plus, I could find the OH minus. Now, if I'm in pure water we're going to say is neutral, so that means it has equal concentrations of H plus and OH minus. And Kw is always this set number, 1 times 10 to the negative 14th. Okay, so since water is neutral, we know it has equal amounts of H plus and the OH minus. Now, if I were to add an acid to water, that means I'm going to have more H plus. So that means that the H plus is going to be greater than the 1 times 10 to the negative 7th, because that was when they had equal amounts. So if my H3O plus is greater than the OH minus, it's going to be an acid. If it's a base, then I'm going to have more OH minus than I did H3O plus. So in that case, the H3O plus concentration is less than the OH minus. All right, so here's a chart. We can see that when it's neutral, I have the same concentrations. If it's acidic, both of these cases, the H3O plus is greater than the OH minus, like that. And then if they're basic, then these ones are both less than the OH minus concentrations. All right, now this one says, what is the H3O plus of a solution if OH minus is 5 times 10 to the negative 8th? So I know that Kw is the H3O plus times the OH minus, and that equals that constant 1 times 10 to the negative 14th. So if I want to find my H3O plus, I'm going to take the 1 times 10 to the negative 14th divided by my OH minus. So I plugged in my OH minus. And for two significant figures, I got 2.0 times 10 to the negative 7th. Right, this one says if lemon juice has an H3O plus of 2 times 10 to the negative 3rd, what's the OH minus? So we know that the H3O plus times the OH minus is 1 times 10 to the negative 14th. So if I want to find my OH minus, I'm going to take 1 times 10 to the negative 14th divided by 2 times 10 to the negative 3rd. And I got 5 times 10 to the negative 12th molar. So that would be C.